Good afternoon. Welcome to the Top 500 Birds of a Feather session. And we're introducing today the 54th list. It is my 32nd SC conference, and I will have a memorable event next year if I still make it. And this is when I'll have more years in my life with SC conferences than without. So that's quite a turning point. With that, I also wanted to look back to SC94, when I believe the first time, so that's also now 25 years ago, or 26 lists ago, that the first Top 500 BOF took place at supercomputing. But with so much look in the back, most of you know what's up the list, and so I'd like to again thank you all for coming and joining us for celebrating the most powerful supercomputers on Earth. And with that, I'd like to just quickly tell you what to expect today. So we will make the first 3 awards worldwide, including the HPCG award, then the Europe, and then the Green 500, and then I will say something about the student cluster competition. And then Erich Strohmeier will talk about some highlights of the 54th list. Wu Feng will talk about the Green 500, and we'll talk specifically about the Fujitsu A64FX, which, and I can spill the beans, is for number 1 and for the Green 500 and is a new architecture. And then we'll go to questions and answers. And with this, I want to turn over and start right away with the number 1 on the top 500 list. And so we are very proud to announce that the number 1 system again is at Oak Ridge National Lab. And I'd like to ask Buddy Bland, Wayne Howell from IBM, and Ian Buck from NVIDIA to come. It's a wonderful collaboration between the Office of Science Lab and IBM and NVIDIA. Congratulations again. But, okay.
And the same team and same system is also number 1 for the HPCG benchmark award. So, thank you.
I'm Jack Dongarra, and I have the honor of presenting the number 2 system in the world. So the number 2 system goes to Lawrence Livermore National Laboratory for having the Sierra system come in at number 2. It's a system very similar to the one at Oak Ridge, not exactly the same. It has fewer number of processors and has a different configuration in terms of the GPUs. And I'd like to ask Terry Quinn, Wayne Howell, and Ian Buck. Terry's from Lawrence Livermore National Laboratory, Wayne is from IBM, and Ian, of course, is from Intel. From NVIDIA. Sorry. Oh, sorry. I'm sorry. I gave away your secret. So here's the certificates, and very well, very good. And I'm going to pass it over to Mike.
And the same pattern here, also the winner of the 2nd place for the HPCG benchmark. So, congratulations. Yeah.
Thank you.
And with that, I like to present the award for the number 3 system in the world, which again goes to the Taihu Light System. And I like to call up Lin Gen and Shidong Sai to accept the award for the number 3 system, the Sun by Taihu Light System. And I have a little list here. Congratulations again. Have a nice collection. Thank you very much. Yeah.
So it is my great pleasure to award the number 1 system in Europe Pete Stein, Cray XC50, is operated at CSCS in Lugano in Switzerland and has been holding the top spot in Europe now for 6 years. Ladies and gentlemen, please join me in congratulating Michele De Lorenzi from CSCS and Dominic Ulmer from Cray.
The Green 500 would like to announce the #1 supercomputer on the Green 500 list is the A64FX prototype. And here to accept the award is 2 representatives from Fujitsu, Naoki Shinzu and Toshiyuki Shimizu, and then from Riken, Satoshi Matsuoka and Yutaka Ishikawa.
Now it's my great pleasure to introduce and announce the winner for the student cluster competition. As you know, more than a dozen student teams from around the world convene here and build a cluster and run the high-performance LinPack benchmark on the cluster. And you see all the teams here. So I want to first give a shout out to all these teams that are listed here. If any of the students are in the audience, please stand up and wave. Oh, there they are. Okay. Congratulations for being here. And now it's my great pleasure, so all of you can sit down again. It's my great pleasure to announce the student cluster competition highest LinPack winner again, Nanyang Technological University, for the 3rd time in a row with a score of 51.7 teraflops. Congratulations. So Nanyang, please rise and get a round of applause. Thank you, and I'll turn it over to Erich for highlights on the 54th list.
Thank you, Horst. Welcome, everybody. Thanks for coming. So I'm going to talk a little bit about what's new, what's exciting in the top 500. Of course, you know that the list now has only petaflop systems. That's been happening this year. I'm going to talk about the new top 10, and there's quotation marks for a reason. A little bit about the HPCG numbers and what we want to do there, what we hope is going to happen in the future there. And then a story which I tried to tell last year, and I think I have a better way of telling it this year. It's been a concise reminder about the NAR scaling, how it has impacted the list, what the type of effects are which we have seen over the last decade in the list. And then I'm going to do and focus most of my attention on most of my time today on something which we haven't done before. Is I'm going to take the list and I'm going to split it in subgroups. I'm going to do a subsampling, looking at the market for scientific computing and the market for commercial computing, and contrasting how different they actually are in terms of which vendors are catering to those markets are successful there, which countries are using those systems for those two types of computing, and which chips they are using. So that's going to be the new part, really new part about the presentation. And then we're going to close it out with the Green 500. But today, Wu is going to give the Green 500 presentation as an introduction for our guest speaker, who is going to talk about the architecture of the new number one in the Green 500. So this is the new top 10. And if you have seen this presentation before, you know that I like to color in yellow the new entries. And if you're wondering, no, it's not your glasses. There is no new entries. So if you're wondering, this has happened twice before. Once very early in the 1990s and once early in the 2000s. So it's not totally new, but it's still something which always comes as a surprise. So the top 10 of the top 500 has not changed, and it's always a question, is there something deeper behind it or not? And I'm further down this slide deck, I have one or two slides where I actually try to look at that in more detail, if this is just another anomaly or if things are actually changing at the top. This is the top 10 in the top 500 ordered by the HPL benchmark. And if I show you the top 10 ordered by the HPCG benchmark, that table is virtually unchanged as well. It has one change, but you can't see it because it was a removal. The K computer in Japan was decommissioned, and it was still, his HPCG results were so excellent that it was in the top 10, actually the number 3, I believe, in the HPCG list. And it has been removed because the computer system has been removed. So the number 10 is new to the list, but only because the number 3, the old number 3, was removed. So there is no new system on that list either. In the color-coded first column just shows which ranks, in which of the systems, the green ones, are ranked higher on HPCG compared to HPL, and which of those systems rank lower than on HPCG than on HPL. So there is some reordering going on, and the last four entries on the top 10 of the HPCG, for instance, are not in the top 10 for the HPL list at all. So the HPCG adds some information. That's all we want to do. That's all we want to see. We are happy that the level of the number of systems in the top 500 with HPCG numbers is slowly growing. It's now 70, but we like that number be much higher. I personally would look forward to do a HPC 100 and actually analyze that, look into what is happening in the HPCG in the list in terms of HPCG numbers. But currently, we don't have enough data for that. But so by any and all means, please continue to measure those benchmarks and give us those. And the same applies, by the way, for power measurements. The top 10 has nothing new. Overall, the list has 100 new systems, lost 101 systems because of the general growth of performance levels. That is low, but not a record low. That is the new normal for the last 4 or 5 years. So that's not very concerning. That doesn't explain the lack of news in the top 10. And if we look at the traditional slide we always show, we don't see too much happening there either in the recent couple of years. So this slide is now getting a little tricky, a little dangerous, because you have to realize that any of these curves is actually now spanning more than 6 orders of magnitude. So if you have a change, if one of those curves would fall behind where it should be by a factor of 2, that's probably already close to the size of the dot I used there. So we have to be a little more careful if you really want to analyze the trends in those lists. And one of the trends we saw at the very first in that list a while ago in 2008 was that the entry level in the list, the lowest curve, was falling behind. It didn't grow as fast as it used to be. And in retrospect, we identified that as being caused by dinar scaling. Dinar scaling broke down a couple of years before that. It took a couple of years till it showed up in the list. But since 2008, the slowest, at least the slowest systems in the list, didn't grow as fast as they used to grow before that. The same effect did not take place in the average or in the top of the list, and that was a little bit of a surprise to us. So there was a second effect which started in 2008, and that effect is related to the average size, the average age of the system we see in the list. So the system, this is not the actual age a system actually has, this is just how long a system stays on the list. So it's related to turnover as well as age of systems, okay? But that age in the list basically doubled from about 7 to 8 months to now 16 months. And I believe it's actually a reflection that not only that the list turns over slower, but that actually our systems are on average also older. To really prove that, we would need to look a little more detailed into the life of system from birth, from installation to decommissioning, which we haven't done, but I'm pretty confident that that holds. So at the same time, when the NAR scaling broke down, we started seeing systems aging longer and longer in the top 500, and the question was, why was that the case? And I already pulled up my interpretation for that, is that we were used to a certain delta increase for a new system when we bought the new system, and if the new system couldn't deliver that delta increase, we just waited a year longer to buy a new one, which actually made our systems older on average. So the slowdown of the NAR scaling led us to delay the purchases of new systems. There was a third effect which started in 2008, which is shown here, which is the effect that the list became very top-heavy. So this is the rank at which end systems have accumulated half of the total accumulated performance of the total list. And we saw that go down dramatically from 2008 to 2013, meaning fewer systems at the top accumulated half the total performance. And the explanation for that is if we really wait longer for purchasing new systems, then if we look at the customer base which can save the money, which they don't have to spend by running their old system a couple of years longer, they have more money in their purse to buy a new system, which then is going to be larger than the old one, over proportionally, at least in terms of dollar. So we would actually expect that in some sense, and it makes sense as long as we can do that. That our aging systems allowed us to purchase over proportional large systems. And when we did that, while we could do that between 2008 and 2013, at the top of the list for the big system, it allowed us to mask the effects of the NAR scaling. So at the top of the list, or the average of the list, we didn't see the NAR scaling really kick in for 5 years, longer than at the bottom of the list, up till 2013. What you see in blue is the year-to-year average performance increase, and you see up to 2013, that was pretty high. And my conjecture is that it stayed high for 5 years longer than the bottom of the list because we purchased systems less frequently, but we purchased larger systems. And this increase in size at the very high end allowed us to keep up performance growth for a couple of years longer, the performance growth we were used to. 2013, that trick broke down too. Our systems were getting too old at that point. We couldn't no longer delay doing that. And the annual performance increase, average performance increase we see in the top 500 dropped down quite substantially. So the top left horizontal orange bar is the performance growth we have seen before. That equates to about a factor of 1,000 in 11 years. The red line is Moore's law, which is about a factor of 1,000 in 15 years. And the new growth rate we see in the top 500 in the lower right, the orange bar, is actually a factor of 1,000 in 20 years. So it takes already twice as long to increase our system sizes as it has done before. So that's the fourth effect which come into play and which made this nice little circle about the two inflection points we see in our traditional curves, which are in June 2008 for the bottom of the list and in June 2013 for the average of the list, shown here as the aggregate in the top 500. So I'm going to go quickly over a couple of slides you have seen in the past just to give you an update, and then I'm going to go to the new statistics. So one of the big effects the last couple of years was, of course, China becoming a big consumer of HPC systems. You see the Chinese market share there going up quite substantially. Has somewhat leveled off. The American share, which has decreased, has also leveled off, and the situation is a little more stable. But again, China is the dominant country to install these systems in the top 500. If you look not at the number of installed systems, but actually weigh the systems by their size, as measured by the HPL Limpact performance, if you look at the performance share, then the United States is actually still slightly ahead of China, at least currently. That's due to the very large system at the very top of the list. And two of those have received the number 1 and number 2 awards today. China already number 2 and not too far behind the United States, and then the countries you would probably expect, Japan and the main economies in Europe following behind. The second effect, which was even more surprising, was that a lot of the systems installed on the list nowadays are actually also manufactured in China. So those are the 3, 4 new and big Chinese manufacturers. China is not only installing systems, but they're actually building their own systems and installing them. And some of the companies from China, especially Lenovo, also are selling outside of China with quite some success, while most of the other Chinese companies are still focused on the Chinese market. They haven't sold outside of China, not in the size that it would enter the top 500, with the one exception. I think Huawei has 1 system in the Arabian Emirates and 2 systems in Germany. Other than that, Lenovo is the only Chinese company currently selling outside of Japan. I already talked about the breakdown in terms of companies. Lenovo is now the number 1 in terms of number of installed systems in the list, and the combined HPE Gray is second, just ahead of Shugon and Inspur. So the Chinese are featuring fairly high ahead of the North American and the US manufacturers. If you look at the same pie chart now, weight by performance again, you see that the HPE Gray chart is much larger, 1. And then you also see the orange chart on the left side pop up. That's the IBM slice, which is, of course, much larger because they sell very big systems in the US. So it's a little more level-headed, and some of the Chinese companies still sell predominantly smaller systems, so they have a smaller slice on this chart. And in terms of technology, steady but somewhat slowish growth of systems which use accelerators or many core chips like Xeon Phi and similar chips. What you basically see is the different generations of NVIDIA GPUs rolling through the list, with now the dominant one being the Volta architecture. But again, that is a trend which hasn't really changed too much from the past. So now to the new part. I want to talk about these 2 different markets. And first I have to tell you how I construct them, how I subsample the list. Have to show you why I think I got it right, and then show you the results about it. So we often get the argument, why did you allow commercial systems in the list? It spoils everything for us who do numerical computing. Of course, we had our reasons, in particular that the commercial markets do have a big influence on which technology we actually can buy and those things. So there is arguments like that. But nevertheless, it is interesting to see how these marketplaces for scientific computing and for commercial data processing are actually different. So to construct proper subsamples, you have to avoid bias. And whenever you do subsampling in statistics, things get tricky. So the way I went about it is I fixed a size, which was 100. And I tried to pull out the 100 largest research systems and the 100 largest industry systems in the list. There's a little caveats to that. So first is for research systems, for the computing systems, I combine the research and academic installations, so universities, as they tend to run similar applications. And for the industry systems, because of a few lists at the beginning of time, I didn't have 100, I threw in the systems which we call vendor systems, which are installed at the vendors themselves. And that is a little shady, but overall, I'm pretty confident that it doesn't disturb the construction too much. We could try to really separate out the industry installations into customers which do floating point and into customers which do data processing, but that is a much more difficult task, in particular because one of the variables which I introduced at the very beginning of the list, I can't find it in the database anymore. I don't know if one of my associates got rid of it because it was too much work to maintain it, but anyway. I ignored the other categories we have in the list, like government systems, which are typically actually data processing systems like IRS, immigration services, FBI, those type of places. I ignored the classified systems because they're classified, so you're not supposed to know what they do. They might be actually closer to scientific computing, but that's not guaranteed either. And I ignored others because that's probably something somebody didn't know what they were doing, so I still don't know what they were doing. And I picked 100 because it works reasonably well. I tried to pick a number which was as large as possible, but I ran into this problem. This is the different market segments as they show up in the list. At the bottom, research and academic. And you see, if I just pick 100 out of research, I have a couple of lists where I don't have 100. And the big blue one at the top left, if I pick 100 out of industry, I'm not going to have 100. That's why I had to do these combinations. So I don't run into sample size effects because I didn't want to deal with that. I could probably push it out to 200, but it turns out that 100 seems to work reasonably well in terms of confidence. So if I look at these two sublists I make, the top 100 scientific computing machines and the top 100 industry machines, where is the number 100 on those two sublists? Where is that last system in the actual top 500? You see the blue line on top, that the number 100 research system is somewhere between a position number 100 and 200. So I'm taking for the research system, I'm taking really a sample on the top of the list out and analyze that. The commercial systems, it goes down between 300 to 400 at some point initially in the list, and has caught up in the last couple of lists with the last commercial system now being around 250. So the one effect both subsamples have is that the very bottom of the top 500 position, 400 and beyond, or even 300 and beyond, basically are not going to influence the statistics. So both of those subsamples are geared more towards the higher end. And then just for fidelity, I ask myself, can I actually replicate the effects, the main effects, which we have seen in the top 500? And for that, I take the typical average system size, which we see in the top 500, and compare it to the average system size in the research subsample and in the commercial subsample. The research systems are higher. That is one of the sampling effects. So the difference doesn't really carry any weight. But they all run in parallel, and that is the good news, because all three samples, the top 500 and both of the subsamples, they seem to show the same growth of performance over time. And because this is average, they actually show the same inclination point around 2013 when we saw the NAR scaling really hitting the list. So that inflection point shows up in all three samples around the same time. And that gives me some confidence that I constructed the samples in a proper fashion, because the overall technological trends are coming out correctly. Then I did the same for the entry-level size. And now, because the entry-level system in the top 500 is much smaller than the entry-level in the top 100 commercial industry, that line is below. And the inflection point we want to see is in 2008. And at first sight, it also looks like those lines are running in parallel, but not quite, because I want to get rid of those 6 orders of magnitude. So what I'm going to do now is I'm going to focus on the right end of the graph after that inflection point in 2008, and just look at that one. So since 2008, since the NAR scaling has slowed us down, we see the last system in those three lists growing roughly parallel. If you ignore the very first 1 or 2 lists, maybe I was wrong by 6 months when I cut it off. But what doesn't quite work is while the commercial and the top 500 graphs, the red and the blue one, they're really running parallel on the right-hand side. The orange one clearly behaves differently the last couple of years, the last 3 years. And there is a new trend there. I haven't checked with a more rigorous statistic how significant that trend is, but for the last 3 years, the entry level, size for the entry in the top 100 research system has fallen behind. So is now at the same level as the commercial system. That cannot be effect of us missing some large systems or anything like that, because this is the performance of the number 100. So if we miss 1 or 2 large systems, that would be 101 or 98, so that wouldn't have a big effect. This is really an effect driven by the size of the systems installed. And what this says is, during the last 3 years, the average size of a research system has really decreased quite dramatically, with a factor of 2 or 3 in terms of size. And we're going to have to see where that comes from and where it leads to. But that's one of the new effects I hope to track in the future about it. So what I'm going to show you now is 6 slides which have 2 pie charts on them. And there are about 3 categories. On the left, you're always going to see the statistic for research. On the right, you see the statistic for the commercial market. And they are color-coded and ordered in the same way. So you can just look at the color, and if the colors look about the same, then the two markets are the same, and if they look different, then the two markets are very different. So this is where the systems are installed, and you see, obviously, the top 100 commercial systems, almost 80% of them are installed in China, while only 7% of the top 100 research systems are installed in China. So it's a totally different distribution in terms of geographically where those systems are installed. If you look at the left, that is more what we traditionally would expect. United States ahead of Japan and then the European countries. If you look at the right, you see the impact of Chinese manufacturing, Chinese companies building systems in China and selling them very aggressively to the Chinese market. And now I can't squeeze 4 of those pie charts on a slide, otherwise I would have done, because I'm going to show you the same 2 pie charts again, but now I'm going to weigh them by performance instead of by system number. So you're going to get an effect, you're going to get more of an information about what the big system, where the big systems are. Same colors, same ordering. So in terms of performance, United States really has still about half of the research systems in terms of performance installed, followed by China and then the other countries. While on the commercial market, while United States and some other countries have a larger share than in terms of number of systems, China is clearly also the dominant consumer of installed cycles there. So that was with respect to countries. The next one is going to be with respect, the next 2 slides is going to be with manufacturers, with vendors. So on the left, you see research, who is building the big research systems. And for this slide, for tradition's sake, I left Cray and HP separate, even though it's one company. So the first 2 slides is the first 2 slices of the pie, is Cray and HP. They are the 2 by themselves, the 2 biggest producers of those systems for the research market, followed by Atos, European company, IBM, Fujitsu, and then the Chinese companies. If you look at the commercial market, it's totally different. All those big companies which sell into the research market, they sell very few into the commercial market, and it's predominantly the big Chinese companies which sell into the commercial market. So the markets are, again, very different. And if we do the same slicing in terms of performance, so we weigh it by size of the system, you see the size effects in the research market that, for instance, HP slice shrank a little, not too much, but it shrank a little, while IBM slice really bumped up because they're selling very big systems. So in terms of performance, IBM is actually the leading manufacturer still in the research market. And the right-hand slide, in terms of commercial market, hasn't really changed that much. It's still the Chinese companies ahead of everybody else. And the last comparison is the one which surprised me probably the most, is if I look now at distribution according to technology, according to chips. And I did a custom slice there, which is basically, I looked at the accelerators and the main processor. And if the main processor is a Xeon Phi or something like that, I put them up separately too. So what you see here, and what surprised me really, is that if you look at the biggest slice, which I just labeled Intel, those are just run-of-the-mill servers. Those are the MPPs. They don't have accelerators, nothing fancy in there. And both markets, both research market and the commercial market, 60% of the systems of the top 100 do not use any accelerators. Doesn't matter which market. It's not like the commercial market is not using its accelerators and all research is using. That's not the case. In terms of the blue slice, those 2 markets are actually the same. That was a surprise to me because, so I looked a little closer. I was looking at that red slice, which is the Intel main chips with NVIDIA GPUs as accelerators. Why is that so large in the commercial market? So I looked at all the systems which are labeled with using NVIDIA chips in the top 100 in the commercial market. And it's constituted mainly of 2 categories. In terms of numbers, it's mostly dominated by anything cloud-based web services, IT services, anything like that. So the Facebooks, the Microsofts, the Amazons, all of those, the Chinese versions of that, that's the red slice. They use GPUs for their server-based web products. There is a second slice in there, which I didn't break out, which in terms of systems is less important, but in terms of performance is more important, which is actually companies especially such as oil exploration, they're using GPUs very heavily, and they buy them in large numbers. So they contribute to the commercial market, because I didn't break out the usage pattern of the systems in the industry into floating point or data. On the left, on the research side, you see that the research likes to try anything out which is promising, and it's a very rich environment. And if we look at the same distribution in terms of performance, it's actually fairly similar with some differences. Again, the commercial market is a similar distribution. The plain MPPs have contributed a little less in terms of MPP, in terms of processing power. But if you look at the research slide, that now has changed simply because of the power slide, the light blue on the left. Because of the very large nature, the very large sizes IBM installs together with the NVIDIA accelerators, that slice is much larger than in the systems category. And particularly the blue and the red slices are smaller. So it's a more varied, more complex picture in this respect. So to summarize my part of the presentation, petaflops are everywhere. That means you have to have a petaflop to get into the top 500 since June. I think this mixture of effects between 2008, 2013, why different parts of the list slowed down at different points. We have now a good explanation for that around in our scaling. We see the beginning of another slowdown, but only in the research market the last 3 years, and we have to see if that's a serious effect and what drives it. It's something I didn't expect to see. And when we break out the top 100 industrial applications, industrial customers, industrial systems, and the research systems, we see that those two marketplaces are very different in terms of what they buy, where they get bought, which countries invest in them, and those things. So I probably think we're going to keep up that separation and producing statistics about that and tracking those markets separately. And with that, I'd like to hand it over to Wu, who's going to give a brief presentation about the results in the Green 500. Wu? Thank you.
Okay, so this is the top 10 of the Green 500, most energy efficient supercomputing systems. What you see is, of course, in the first column is the listing of the supercomputer. There's 3 columns in the middle that are not labeled, so that's the processor, the CPU processor is the second column, the third column is the network interconnect, and the last column is the accelerator that's used. So what the first thing that should strike you is that it's the A64FX prototype is the only one that does not have an accelerator. And we'll get back to that in a little bit more detail, and then have a representative from Fujitsu discuss some of the details of the A64FX prototype. You'll see that A64FX prototype is not the only new supercomputer. There's the NA1, Amos, and Satori. These are accelerator-based systems. You can see that the PEZI SC2 accelerator that's used in the number 2 system, and the NVIDIA GPUs that are used in the IBM power systems, AC922s. The rest of the list is largely the same. There's a note that if you see a couple of the asterisks off to the right, I don't know if I don't have a... the AI Bridge Cloud Infrastructure ABCI, as well as the Tsubame 3.0. These are systems that also submitted a power-optimized HPL run. And what that does is you have to run the same size problem on the same size machine, but we're allowing software innovation with which to make a more energy efficient run, and that's reflected in the ABCI and the Tsubame 3.0 architecture. So with that at a high level, I'm going to look at some other high-level trends that we'll dig more into in the Green 500 BOF, which will be on Wednesday at 5:15 to 6:45. So we take a look at this diagram. Whoops, sorry, thank you. What we see here is this is the trending lines for the Green 500 rank for the top supercomputer in red, the mean in green, the median in blue, and the bottom Green 500 machine in purple. I'll just draw your attention to the machines in on the top of the Green 500. What you see is that there's plateaus, if you will, or stability points. We see that back in the late 2000s to the early 2010s, we had the cell broadband accelerator that topped the Green 500 list. That then evolved into a non-accelerator based, low frequency, low power, massively parallel processing system from Blue Gene, the IBM Blue Gene systems. Then we had another transformation to the GPU systems, in particular Tsubame KFC, the K20 X GPUs accelerators. And so on. And what you see more recently is the Shobu B with a PEZI SC2 accelerator with the next plateau. And the A64FX prototype is right around the same gigaflops per watt in terms of performance. Now, with that in mind, I wanted to point out a couple things. Is that so many of you that have been around SC for a while and think back to the mid-2000s, mid to late 2000s, that line that I'm showing there is the DARPA exascale study that was projected what an exascale system in 20 megawatts would be. Exascale system in 20 megawatts is 50 gigaflops per watt, and that's where that mark is. That projection got later slackened and said, well, by 2018, we would get to an exascale in 20 megawatts. This was several years back. And now it's not clear we will get to exaflop. It's not clear that we're going to get to it in a 50 gigaflop per watt efficiency envelope for 20 megawatts total. We've been hearing, of course, systems. The system in China projected to be upwards of 30 megawatts, and our own in the U.S. that there's 40 megawatt systems, and so this is just to get an idea that power is really an important aspect in these powerful supercomputing systems, and we've been kind of pushing the timeline farther and farther out in terms of reaching an energy efficient solution. I'll also take a moment here to point out that that the animation with the arrows, and we went off the side. Some of you may remember back in 2013, my esteemed colleague here, Horst Simon, he made I think it was a $2,000 bet, Horst, right? He made a $2,000 bet that there would be no exascale in 2020. Is that correct? Yeah. And so we'll see if that comes to fruition or not. The expectation is that it will, of course, based on the announcements that have been made. So with that, one of the things that you should see here is that I went through these plateaus in that top tier, and in all of those plateaus, not all of them, most of the plateaus, they were accelerator-based systems that were the most energy-efficient systems. The exception was the Blue Gene system, which focused on low power, low clock frequency, kind of massively parallel MIMD processors. And now we have the A64FX. Did they take the same approach? And you'll hear a little bit more about that from Toshiyuki Shimizu in a bit. But I'm going to kind of prime the pump, or maybe give you a little tease in terms of an outsider's view and looking at it through a certain lens. Let's start here by looking at these trends in energy efficiency. I've zoomed into the last 6 to 7 years, and what you see in the orange are the systems that are heterogeneous. These are the accelerator-based systems, the cell broadband, the GPUs, that PESI SC. In the yellow, you see the homogeneous systems, and then the green is all the systems. And what this is a classical box and whisker plot. The middle quartiles in each of the boxes are the second and third quartile, and then the whiskers represent the other quartiles. And the dots are the outliers. And so what you see is that, you take a look at about 2017, you can see that the accelerator-based systems really start to dominate in terms of the energy efficiency, in terms of gigaflops per watt. And the homogeneous systems in the yellow boxes, you see how much lower they are in terms of their energy efficiency. They're not particularly energy efficient, and that's part of the reason why we see this enhancement in the energy efficiency of the accelerator-based systems. And so one thing to see here is that the improvements on the high end have been much more dramatic, and that's why you see so many of the dots and the outliers that are higher up. What's particularly notable here is that circled dot right there, right? So all the dots before that, all the outlying dots that you see before that, most of them were categorized with the heterogeneous systems, and when you put them all together, the heterogeneous systems are the ones that contribute to all of the most energy efficient systems. But that dot there, that single dot there, is the A64FX prototype. It's way, way, way off the chart relative to the box and whisker plot that you see for November 2019. And so the first thing you do is, as a scientist, just like, well, wow, this is just amazing. How could this be possible? And I'm not going to say that I have all the insight because, but in looking at it at a high level and going by the Fujitsu booth, I'd invite you to go there, and there's information about this, and so that information, I'm not saying that the efficiency is all due to this, but when I saw this slide, the first thing that drew my attention was the peak memory bandwidth. Okay. So think about your traditional CPUs and what the memory bandwidth is. You're talking about 100, 200 gigabytes per second, right? And if you look at the GPUs, they're supported by very large memory bandwidth, 900 gigabytes roughly, 900, maybe 1,000 gigabytes per second. And this is what you notice here. This is not an accelerator, but it's the large memory bandwidth has been brought to the CPU. Now, there may be there are obviously many other reasons why this is so energy efficient, but this is one of the things that jumped out. With that such large memory bandwidth, with many of the applications, you can get a better performance on your applications, given that you'll get more flops per byte of information. So I'm not going to get into the details of that. I'm going to defer that to our speaker. What I will want to say and close here, a lot of the the graphs that I showed, the trends, there's many more, much more analysis about them relative to exascale and the 50 gigaflops per watt target for a 20 megawatt supercomputer. So I invite you to the Green 500 BOF that is chaired by myself, Erich Strohmeier, Natalie Bates, and Tom Skoglund. It's called Green 500 Trends in Energy Efficient Computing. It's tomorrow at 5:15 to 6:45 in room 503. You'll learn more about the history of the Green 500 and the empowerment methodologies that come into play. And we'll have more detailed talks from the A64FX prototype folks. I've put MicroFuga kind of in double quotes there because it's a prototype that looks to be part of the larger Fugaku supercomputer. And then the Green 500 #3 supercomputer, which is the #1 academic supercomputer on the Green 500 list called AMOS. And you'll see more detailed analysis on the Green 500, including trends of the past and present to the future tomorrow. So with that, I'd like to cede the stage to the folks from AFX prototype. I'm going to again call it MicroFuga. This is please come up to Toshiyuki Shimizu. He's the Senior Director of System Development at Fujitsu Limited. Thank you. I think you have to...
Good evening, everyone. I'm very pleased to have an opportunity to present our result for the Fujitsu A64FX prototype. So just start. This is my outline of my talk. I showed our achievement and how Fujitsu worked, and then I introduced the Green 500 measurement conditions and supercomputer standard and our futures. So as you know, this Monday, so Green 500 is disclosed, and our machine A64FX is received the #1 as a machine without accelerators, only with 768 general purpose A64FX CPU. It is very different result compared to the rest of the 500 history. So 2 petaflops and 16.876 gigaflops per watt. Okay. This is a result of Green 500 and Green 500 ranks and top 100 editions, where is the first machine is ranked. Okay. As this, do you distinguish between the orange and blue? It is very easy. The system with accelerator or without accelerators. So as introduced as by Wu, so A64FX prototype is the system without accelerators. So the second grade and third grade, all machine at the high rank is with accelerators. Where is the second non-accelerator system is? Here, somewhere from right. Up here, this is 6 gigaflops per watt. This means that approximately 3 times better gigaflops per watt to second system as Typhoon Wright. And this is appeared at the 48th edition of Top 500. So this means that our machine supersedes the record of the system without accelerator after 3.5 years. This is very epoch-making result, I believe. Okay. Okay, so I thought that Endeavor was the first grade without accelerator, but I will check the results. So I noticed that the Wu's explanation today, so I will check that. Okay. Okay. The next. So this is a result of the top 500 ranking and gigaflops per watt. So our machine, A16-4FX prototype, is very high area, and another system without accelerator is very low numbers. So this is a view of the top 500. Okay. 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 So I'd like to explain about how Fujitsu did. I believe that the key for the high energy efficiency is energy efficient hardware and Sofia Technologies. As you know, A16-4FX is developed for Fugaku and our supercomputer product, focusing on the power efficiency from the scratch of the development. We use our proven CPU microarchitecture into our CPU design, and also use leading edge silicon technologies, 7-nanometer FinFET technologies. And we use SoC design. We integrated TOF interconnect D into our CPU chip. Also, we use CAWAS technology to integrate the main memory 4 HBM2 into the CPU package. There is no additional parts is required to make the system. So A16-4FX is a very power efficient system in nature. As for the Sofia Technologies, Fujitsu optimized the math libraries for application efficiency for a long time, not only for the LIMPAC or HPL. And communication libraries are also tuned utilizing our long experience of the TOF interconnect. It was developed for the K computer. We have long experience. So lastly, our performance tuning environment is very easy to tune the performance. This is the reason why we can get the good numbers. So we show some numbers of results. So this graph shows the NMAX, or problem size of HPL, and calculation efficiency. You all know about the HPL problem. So large problem size is easy to get the high efficiency, calculation efficiency, but very difficult to get the to get the high performance for the small number of problem size. But we achieved that the high performance or high calculation efficiency with small number of NMAX. So this is the reason why we can use the optimized communication and math libraries and our performance tuning environment. Okay. So I will show some measurement conditions of our machine. This is the system configuration we use for this measurement. You can see that 2 racks center having the 780, 16.8 CPU, 2-rack system. We measure the performance using these 2 racks, and measure the power consumption of the 1/4 of the system. Okay. So this is a machine located at the Fujitsu Numazu plant. very close to the Mount Fuji. So this is a coincidence of the Fugaku. Fugaku is the name of the Mount Fuji, and the location of our plant is close to the Mount Fuji. And this measurement equipment. So this is a log of the power consumption during the calculation, full run. You can see that the very smooth power consumption logs. This also shows the efficient calculation through the core phases. This is a good performance tuning is done. Average of core phases per consumption is 118 kilowatt per system, 2 rack. And idle power is also very low, 50 kilowatt per system or 2 rack. Very power efficient system. So I'd like to introduce our machine for the basing on the A16-4FX prototype. So this is Fugaku images. So Fugaku is named after Mount Fuji, and Mount Fuji is the highest mountain in Japan and very broad gradual slopes. So Fugaku is designed for the high application performance and high power efficiency and usability. I think that we can prove the high power efficiency through this conference. So this is an image of the Fugaku rack. And this is our commercial product, Prime HPC FX10 and FX700. Very fancy slide from the commercial department. Okay. This is a Cray machine. Recently announced the Cray introduced the Cray CS500 using our A16-4FX CPU. This is very important. And I will show my opinion. It's my opinion. Okay? Energy saving is primary social issue for the future, even now. So greenness is not only for the environment, but also good economy. This is also important. Economy is very important. And power consumption or cost of electricity is a major part of TCO of supercomputers. So we have to be more conscious for the supercomputer power consumption. Green 500 is very good benchmark and will be more important. However, so only 43% of the system report its power consumption to submit the top 500. So we need more recognize the importance of the power consumption. I would like to propose to that top 500 to better to ask to submit power consumption mandatory. So this is my thought or my personal opinion. Okay? Okay, so this is a summary. So A16-4FX prototype, the prototype, MicroFuga is achieved number 1 for the Green 500 and ranked at 159 in the top 500. This is very good result for us. We are very happy. And general purpose A16-4FX CPU will be widely used by many customers from Fujitsu directly and through many partners. So the supercomputer Fugaku will be operated by Riken and Cray CS500 will be distributed by Cray or HP, and Fujitsu also provide Prime HPC FX1000 and 700. So please come to the Green 500 booth tomorrow. So meet there. Thank you very much.
Thank you, Shimizu-san. And we are now coming to the question and answer portion of the booth. There are the microphones in the aisles labeled from 1 through 5. So if you do have a question about the Fujitsu A64FX prototype, about the top 500 list, please line up behind the microphones and I will call you, and please state your name before you state your question. So on number 4, we have a question.
Hi, my name is Ahmed Abul Fitu. Very nice presentation from Fujitsu. You mentioned that you didn't use any accelerator in your system. Do you see any value if you start using accelerator in your system? Do you think that number of silicon will be reduced, the cost, the efficiency? Do you see any value to start checking if you add accelerator to your system?
So, okay. Okay. So we designed or we developed the H64FX for Fugaku system. So Fugaku system is a center machine for many applications. So there is limited applications that will perform on the accelerator, with the system with accelerator. So we have to use hardware or invest almost all for the applications, everyone. So we think that the general purpose CPU only system will be suited for the such center system, the center for excellence or large systems. And it is yes, that's it. Is that the answer for you?
So just because you would like to create a machine to be a general purpose, that you don't want to use accelerator in your machine, right? Thank you.
Is it live? Yeah. So I'm probably going to overspeak a little bit here, and I can Fujitsu and Erich can correct if it's necessary. But it almost seems to me that you've taken on some of the GPU ecosystem and it's been put onto the CPU. So think about the memory bandwidth is massive, okay? And then there's vectorizing instructions on the CPU that is in some sense a form of an accelerator. So one might argue that you've taken the GPU accelerator SIMD processing and plopped it onto a CPU. There's a gross, very coarse-grained characterization, but you've plopped it onto a CPU with MIMD processing.
So I think that the programming for the accelerator, different LSI or different memory. Different memory is still difficult for the many research areas. So the machine of the Fugaku is for research purpose. So we don't ask the programming or performance tuning, but also we ask the researchers for research itself. So difficult programming is not good for such machines.
Okay, another question on number 3, Vladimir.
Vladimir Getov, yes. Indeed, very interesting. I guess we can keep talking about your design for the rest of the evening, but in your presentation, you always mention prototype. What is going to happen when you remove prototype, and how far are we from this time?
Okay, good question. So we call the machine prototype is only for the produce the phase. So we developed or produced earlier than Fugaku system itself. So we install the machine earlier than the Fugaku system. So we call it the prototype. Just the same design and the same, how can I say, configuration.
All right, thank you.
Okay, are there any other questions? I don't see anybody lined up at the microphones. If not, then I would like to suggest we give a round of applause to the winners of the Top 500, Green 500 and HPCG lists, and also thank our speakers. And I wish you all a good evening and a successful rest of the conference. Thank you.